Alright, if you're watching this, then you feel like you need some more help, and here is another problem where we're launching at an angle. This one has a few more steps to it. We have a salmon that jumps the waterfall to reach the breeding grounds. It starts 2 meters from the waterfall, that is 0.55 meters tall, and jumps at an angle of 32 degrees. What must the salmon's minimum speed be to reach that waterfall? So let's go ahead and write down what we know. So we know that the delta x is 2.00 meters. We know that the delta y we need to reach is 0.55 meters. And we also know we have a theta of 32.0 degrees. So how do we go about solving this problem here? Well, we are missing a few things in this problem. The first one being we do not have a time, and we do not have the velocity. Looking at our equations, our general equation again is the change of distance is VI delta t plus 1/2 AT squared. Well, if we go again in the y direction, we can solve, let me put down a couple more knowns. Remember that the acceleration in the x direction is 0. And we have the acceleration in the y direction is negative 9.81 meters per second squared. Other equations we can look at for this type of problem are, we can look at the v final velocity is the initial velocity plus AT, or we can look at the velocity squared final is equal to the velocity initial squared plus a change in your distance. So analyzing which problem to use, let me walk you through this. If we were to use the first problem, we have the distance, we don't have the velocity or the time, so there is just way too many unknowns for that one. This one here, we have the final velocity would be 0, the initial velocity we don't have, and we don't have time. Again, too many unknowns, which means this one's probably going to work out. As your fish jumps up to the waterfall, we know that it has initial velocity in the y direction, and the final velocity in the y direction will be 0, because that will be at the midway point of your whole parabola. So using this equation here, we have this. We do not have the initial velocity. We have acceleration in the y direction, and we have the distance in the y direction. This gives us one unknown, and therefore identifies this particular equation as the best equation to use in this situation. So now let's write down our equation. Notice that everything is now in terms of y. Y, y, y. We're only looking in the y direction. You have to keep the x and the y separate. So let's fill in what we know. The final velocity is going to be 0. The initial velocity is going to be vi sine of your theta, which in this case is 32, squared plus 2 times negative 9.81 meters per second squared times your distance, which is 0.55 meters. When you have two things multiplied together with a square, you can distribute the square and rewrite this as vi squared sine squared of 32 plus 2 negative 9.81 meters per second squared times 0.55 meters. At this point, let's put some stuff in our calculator and see what we get. Alright, after the first step of typing it into the calculator, we get the sine of 32 squared is 0.281. That's still going to be multiplied to our vi squared. And then when you multiply 2 times negative 9.81 times 0.55, you get a negative 2.70 meters squared per second squared. Now we are going to subtract this 2.70 from both sides, and that will give us a slightly nicer looking equation of negative 2.70 meters squared per second squared is going to be equal to your vi squared times 0.281. We can then divide this 0.281 on both sides of the equation, and that gives us vi squared is equal to 9.60 meters squared per second squared. Now we want vi, so we can take the square root of both sides. And remember, vi is now 3.10 meters per second. So that means the fish must travel at least 3.10 meters per second in order to reach the waterfall. Now, even though the problem didn't ask for it, we could step this up and find the time that it would take for the fish to reach the waterfall. Because now we know the initial velocity and we know the direction in the x, and we can calculate the velocity in the x direction, and by doing all of that we can actually calculate the time it would take. So let's write down what we know. Vi is 3.10 meters per second. We know that our delta x is equal to 2.00 meters. We know that a in the x direction is 0, and we know we have a theta of 32 degrees. This is all the information we need to solve for the time, because in the x direction we need Vix times time plus 1/2 axt squared, which this part here is 0. So the only thing we really need in order to solve for time is this VIX. We can easily do that by using our component vectors. If the initial velocity is 3.1 meters per second, our VIX is going to be 3.1 cosine of our angle, which is 32. Putting this in your calculator, you get a VIX of 2.63 meters per second. Now let's put in what we know and find ourselves a time. So that is delta x over VIX is going to give me my time. That means we have 2.00 meters over 2.63 meters per second. Plug that in your calculator. And we easily can now find the time of 0.760 seconds. Hopefully you're catching on to these, and I'll try to put another one on if need be, but work these over and over again, and practice makes perfect.